both me and the TA grading the exam question. So if I have any questions that need to clarify, I can ask the TA directly. Okay. All right, so we finished the file system for or general file system. Right? We did not get to talk about the Linux specific file system, but we will come back to that later. I think with the lecture content on the general file system, you should be able to work out the labs by yourself. The lecture content that we want to cover right now is the device driver. Okay, so after we finish talking about device driver, we will go back to Linux file system and wrap that up. But let's first learn device driver because the underlying disk read and writes, network card I/O, and this layer underlying the file system, right, is implemented using device driver. Okay. So if you trace your file system operation, you might be able to, right, in the end, trace to device driver. So it's important, right, to understand device drivers. Okay. So, but before we dive into the detail, right? So we'll start with what is a device driver. Right? So for every hardware device that your computer uses, right, this device has an interface that you can use to communicate and control this device. Every device has different interface. You can imagine that your disk and your keyboard and your monitor, your computer monitor, or the projector, and these devices have a very different interface. Okay, and also when you, for example, when you go to a printer shop, right? When you connect to a printer, sometimes your computer would pop up a notification saying that you need to install some device driver in order to use the printer. Okay, so that device driver is the interface your OS communicate with. Right? Your OS and the user application can interact with this device driver. And the device driver is responsible for controlling the hardware device directly. Okay. All right. So the point of this is that you want to hide the hardware device implementation details. Right. So every hardware have very subtle implementation details that if exposed to user application, it can be confusing. So, right, to make the user experience much better, most hardware device vendors, they provide the device driver themselves. Right? So, yeah, if you get a new piece of hard drive, if you get a new printer and you put it at home, okay, and sometimes you need to install this device driver, and you download these device drivers from those companies' website. Recently, I bought a new printer and put it at home, and so I had to download the device driver from the company's website for that specific device. Okay, that is device driver. And so you can imagine that there are many device drivers that comes natively with your OS, right? So the keyboard and monitor, right? So these device driver come natively with your OS. So when you start the OS, you can start using your keyboards directly. Okay. All right. So device driver used to be a very hot research topic and also very hot even engineering project topic. Can you imagine why is device driver so difficult to get right? So the research around device driver is mainly how to make it correct, how to make it perform better, and how to avoid errors in device driver to crash your OS. Right? These kind of topics. Can you imagine why is device driver a hot topic for OS research? There are a lot of problems that exist in device drivers. The reason is relatively straightforward, and the reason is that these device drivers are all in control of the OS developers, and there are many of them, right? So in these commodity computers, right, there are tons of device drivers, and each device driver is written by different developers from different companies. They don't have a standard, and they could have a lot of bugs, and because these device drivers are installed inside the OS, it could crash your OS kernel. Right? It's not like a user application. If a user application crashes, it's just a process, right? It's a user process crash, and you just swap it out or just kill it. But very often, in most modern OS, right? So these device drivers are still inside the OS itself, and crashing a bug in this device driver could crash your entire OS. Okay. I'm not sure whether people, students nowadays know there was a very famous interview with Linus Torvalds, the creator of Linux, and in that interview he basically spent a long time just talk bad things about NVIDIA at that time. NVIDIA right now is huge, right? So at that time, NVIDIA was just a graphic card builder that its revenue is mainly from game players, right? So build high-end video cards for game players. But even back 10, 20 years ago, NVIDIA already started their, so they adopt this closed source strategy. So all of their internal, like their GPU design, their device driver, everything is closed source. And there are a lot of bugs. Right? It's very buggy. And Linux community, and Linus Torvalds himself complained a lot about NVIDIA. NVIDIA graphic card GPU at that time was already very popular because the performance is good. It's just everything is closed source, and the device driver is very buggy. And the entire interview, right? So so Linus Torvalds spent the entire interview talk bad about NVIDIA. That's how bad device drivers can be, right? So how much problem device driver can cause you, okay? All right. So of course nowadays no one is complaining about NVIDIA. Everyone wants to get GPUs, and everyone uses NVIDIA's CUDA software stack. Okay. All right. So we're gonna explain device driver, and we're gonna go through some simple device driver, one simple device driver, how it is implemented in Xenu. Right? So it is conceptually very simple. It's just a console. Right? You can send a character to this console device and then read a character from this console device, right? And then you can, based on this simple interface, you can send a sequence of characters to this console device, and you can read a sequence of characters from this console device. Right? That's the main functionality of this device. So conceptually very simple, but the implementation is not trivial. Okay, we'll start from the high-level concept of device driver. Okay, and so the device software have three conceptual pieces, right? One is the abstract interface. This is the interface your OS interact with this device software, right? And a set of physical devices, right? So the keyboard driver, right, interact with your keyboard. Right? Keyboard is a physical device. Okay, the interface provided by the keyboard driver is an abstract interface, and device driver that connects these two. Right? So the device driver provides this abstract interface that your OS uses, and it manages this physical device to provide this abstract interface. Okay. All right. Yeah. So every device driver can be divided into two parts. So its definition, right? The conceptually is very simple. One is called upper half. That's the application and OS can call directly. Okay. The other is lower half that handles interrupts. This is straightforward to understand. Right? When you use a console or some I/O device, the user application can send characters or send outputs to this device. Okay. That is upper half. The application and OS, we can both use this interface to send things to this device. You can also use API to wait, right, to wait on some output from this device. That's also wait on some input from this device. That's also possible. Okay, those are upper half. So the OS and application use this interface to directly invoke the this device functionality. And the second is the lower half. The lower half is what the interrupt invokes. And remember that every device is registered in your OS, and every device registers one interrupt, right, in the interrupt handler vector. So whenever this device raises an interrupt, this interrupt handler specific for this device will be invoked by the OS. Okay. For example, if you have a disk and you perform a disk I/O, and when this disk I/O is finished, the disk itself will raise an interrupt in your computer hardware, right, on the bus, and this will be detected by your OS, and your OS will search inside the interrupt vector to find the corresponding interrupt handler for your disk device. Right? In comparison, if it's a keyboard, if you push a key on your keyboard, this also raises a interrupt. Right? And when this interrupt is captured by your OS, it will search inside the interrupt handler vector and find the interrupt handler that specifically handles keyboard interrupts. Okay, that interrupt handler, right, is the entry of the lower half of device drivers. When the keyboard interrupt happens, keyboard interrupt handler is an entry to the device driver of the keyboard. Okay. All right. this is a diagram showing this the upper half and the lower half. Upper half and lower half are just conventional names, right, that people call them in the very, very early days. But the key difference is you can just remember that the functionalities and the interfaces, application and OS directly call, right, they directly invoke. Those are upper half. Right? And there's another set of interfaces that is triggered by the interrupt itself. Right? The hardware interrupt triggers these interrupt handlers. They are called the lower half. Okay. So this part of the upper half, this part of the interface is to handle application requests. This part of the interface, lower half, is to handle the hardware response or hardware initiated actions. Okay? Does this make sense? Upper half, invocation to upper half is initiated by the application. Invocation to lower half is initiated by the device, the hardware device itself. Okay, so that is like the difference between upper half and lower half. Right? Yeah. So these two abstractions are needed because the I/O interface the OS offers to the applications. Right. This is the upper half, and the second, the interface offered by the underlying device driver functions. This is the interrupt handler. Okay. Goals for the device interface application uses. You want this device interface to provide isolation from hardware. Right? Ensure that the applications do not contain details related to the device hardware. Why is this important? So this isolation is a really implementation level isolation. You want the application to be able to use your device without knowing the internal detail, the hardware features of your device. Why this is important is because if you achieve this, then your application, user application is much easier to write. Okay, so when you write your user application, you do not need to read every hardware device menu, right, to understand how to use this hardware device. Okay, so yeah, isolation from hardware. Right, so your device driver want to provide an interface that is general, that is high level enough, that it does not contain details related to this specific hardware. Okay, and this also provides portability. Right? If this device driver provides higher level abstraction, then it allows applications to run any brand or model of equivalent device unchanged. Right? You can imagine that, for example, I think the simplest example is that sometimes you install one device driver, but it works for different models, different hardware devices from the same company. Right? The internal hardware details are different because you are using different hardware devices, right? Even the simplest example, GPU, right? So from NVIDIA, they have a series of different GPUs. But you install CUDA, and CUDA handles everything. Right? So the benefit, right? The benefit of the goal of this is that you want to design a high-level interface for your device driver, so that it is portable. Right? Allows applications to use your device driver without worrying about the underlying hardware. Right? underlying hardware, as long as they are supported by this device driver, they can be swapped arbitrarily. Okay. Elegance, right? Limit the interface to a minimal number of orthogonal functions. Okay? So yeah, when you build this device driver, you want it to be minimal, to be simple, to be elegant. Okay. Generality, right? Use a common paradigm across all devices. This is a different goal. This is interesting, right? So this is another goal. Ideally, we don't just want to hide the, for example, GPUs under one device driver. And if, let's say, the device driver of GPU and the device driver of keyboard and the device driver of projector, they are very, very different. They provide very unique ad hoc interface. Then it's still very difficult for you to write applications to use them. Okay, so what is so that's why when developers or OS designers design the device drivers, they try to make sure that most of the device drivers they support similar set of APIs. Okay. Yeah. So the usage of these APIs are also very similar, although when it's applied to different, implemented on different devices, the guarantee is slightly different. Right? But later we'll see that this set of APIs are supported on almost every device. Okay, and integration, right? Integrate the device manager with the process manager and other OS facilities. Right? So you need to make sure that the OS can invoke these device driver interfaces and the interaction with OS native functionalities like process manager and other OS facilities are correct. Yeah, these need to be carefully integrated. All right. So how to achieve these goals? Right. We devise a small set of functions that application uses to obtain incoming data from a device and transfer outgoing data to a device and control the device. Right? So these two things, obtain incoming data and transfer outgoing data. Right? If you work in the OS for long enough, you might see this pattern happen repeatedly. Right? Byte stream, incoming data and outgoing data. Both of them are usually formulated as a byte stream. Okay, and that is the abstraction almost all device drivers support. Every device can be treated as if it is a byte stream. Right? So your monitor is a byte stream. Your monitor, you're sending bytes to your monitor, and you are there might not be it depends, right? So if it's a touchable monitor, it can also send data to your OS. But if it's like older traditional monitor, you only send data to your monitor. You're not receiving things from it. Okay, so it provides the same interface, but the main functionality of monitor is you're sending a byte stream to the monitor. Okay, your keyboard is mainly for reading, receiving incoming data from your keyboard. Right? It still provides these two interfaces, right? So an incoming byte stream and an outgoing byte stream, but most of the time it just uses this incoming byte stream. Right? Your disk and memory, they are also formalized as modeled as a byte stream. You can write a byte stream to this your disk. You can read a byte stream from the disk. Okay, This is a generic interface of device drivers, byte stream. Okay. And control, right? Control, this interface is going to be a little bit more ad hoc, right? Because every device is controlled differently. Right? You can imagine the control of a keyboard and the control of a monitor, your screen will be very different. Right? The control of your keyboard might mostly be idle, and the controller might be just busy pulling, right? Every time in an infinite loop pulling whether there's any signal sent from your keyboard. But the screen, your screen or monitor, is the control should be very different. Okay, later we'll see an example of a simple device driver. And so this control is more ad hoc. The data interface is more generic. Examples of control, you can adjust the volumes in your headphones. You can turn off character echo when reading a password, so your passwords do not show on the screen. And you can eject a CPU device, CPU drive, right? So these are examples of control. So that it also shows that control is an ad hoc interface of device drivers. Okay, the data interface is unified. The control interface, how to perform control, can be very ad hoc. Okay, yeah. So the approach is known as device independent interface, but the part that is really independent is the data interface. The control interface is not really device independent. Okay. Yeah, so how to achieve this device independent I/O? Well, we define a set of abstract operations and build function for each operation, and have each function include an argument that programmer can use to specify a particular device, and arrange an efficient way to map generic function onto code for specific device. This is a high-level procedure, how you develop, design a device driver for your hardware, right? Suppose you develop implement a new hardware. This is the procedure you follow to implement the driver for yourself. Okay. Yeah, defining a set of abstract functions is very mostly is straightforward, because you define the data interface almost the same way as other devices. It's just writing to a byte stream, reading from a byte stream. But the difficult part is the control, right? So you need to really think hard how to implement your control interface clearly. Okay. All right. Yeah. So a set of a device driver consists of a set of functions that perform I/O operations on a given device. This code is device specific, right? Because performing an I/O operation on different devices are very different. Okay. And this set of functions include an interrupt handler function and what it invokes. And this is the lower half. Interrupt handler function and whatever the part it invokes inside the device driver, this is the lower half. Okay. Functions to control the device, and this is used by the application. Functions to read and write data, this is also used by the application. Right? These two are the upper half. The upper half of the device driver is used by the application. The code is divided into two conceptual parts. Yeah, so the upper half is the functions that are executed by the application and perform data transfer, right? Read or write. Okay, and the code will copy the data between the user and the kernel address space. Okay, the lower half is evoked by the hardware when the interrupt occurs. It consists of a device-specific interrupt handler and we also include dispatcher code, right? And yeah, so we restart device for the next operation. We already explained the difference between these two, the upper half and lower half, in the previous slides. Okay. Yeah. So how to divide the duties in the device driver, right? What should be the upper half responsible for, and what should be the lower half responsible for? So the upper half should have minimal interaction with device hardware, right? It should incur a request, and then we'll see, okay, hardware device, whenever you are ready, right, get its request and do the data transfer. That's the main responsibility of the upper half. Whenever the application uses the upper half, usually it puts this request, maybe read or maybe write into a queue, and let the device know that, okay, whenever you're ready, perform this IO. Read or write. That's the upper half. Okay. The lower half have minimal interaction with the application. Right? You can imagine the lower half is whenever there is an interrupt raised by the device, it will go and check. Maybe there is some request, read or write request in the queue. And you can go ahead and perform that read or write request. Okay. So its goal is to have minimal interaction with the application and interact with the device to obtain incoming data or send the data out, right? Depending on which request is in the queue. Okay. Reschedule if a process is waiting for the device. Okay. Just to make sure that the device is multiplex, is really used by different processes. All right. So this is an example of the APIs provided by a device driver. This is in Xenu. In Linux and other more complicated kernels, the interface can be more complicated, but in Xenu it's very simple. Right? So you have a close, which closes this device and prevents it to be further used. You have a control operation. It performs operations other than data transfer. Right? We will talk about this control later. Right? This getC is to input a single byte of data, get a char. Right? Initializing the device, right? Seeing that okay, there are some setup work to be done for the device, and let's finish all the setup work. The simplest example of setup is that I might need to allocate a buffer or a queue or a buffer pool for this device, right? So that the application can use this buffer pool to read and write data. Okay, initialization could be responsible for this. And open, right? So if a process calls open the device, it's going to use this device for future operations. Data read or write. Put char, right? Put C, outputs a single byte of data to the bus. Read, right? Input multiple bytes of data, and write, output multiple bytes of data. This is compared to getC and putC. And seek, move to a specific data. Right? Okay. Now, I don't want to pause here to explain that this interface is generic. Again, okay, it's used for many different devices. Okay. The reason is that in Linux, in Unix style systems, right, we treat devices as byte streams. And because we treat devices as byte streams, so to operate or to manipulate this byte stream, we at least need to have get char, put char, read, and write. Put char is writing a byte into the byte stream. Get char is reading a byte from the byte stream, and read is reading multiple bytes. Write is writing multiple bytes. Okay, so these four interfaces exist because we treat every device as a byte stream. Seek is also the same, right? So if you treat the device as a byte stream that is not just consumable, but just exists there, right? Like a big array. Usually, the disk is abstracted in this way. Then you can perform seek, which is to move the index, the current index, to some location in this byte stream. Okay, move the index to some location in this array or byte stream. That is a seek API. Right? These 5 APIs, they are there because we model devices as byte streams. Okay. All right, but think about this, right? So I think I already gave some examples, but I want you to realize that this is an intentional choice. It is very general, and we have explained that your monitor can be modeled as a byte stream, although most of the time it's only sending data. It's only used to send data to the monitor. Right? It's mainly an outgoing byte stream most of the time, but it can be modeled as a byte stream. Your keyboard can be modeled as a byte stream, although most of the time it's just an incoming byte stream. Right? Your disk and memory, they can be modeled as byte stream. Right? When you are reading things from disk, writing things to disk, right? So you can consider at least input and output, they are all byte streams. Okay. Right. So every device needs to do I/O, right? Need to interact with your computer through I/O. So that's why the generic interface of device drivers is byte stream. Okay. Even file, right? In Unix, I guess in Unix philosophy is everything is file, right? So if you have heard about it, right? The file, what is a file? Right? File in Linux is or in Unix is again a byte stream. Right? So everything is actually modeled as a byte stream. Okay. All right. So open and close is a standard. The only thing that is very ad hoc is this control. You will see that this control API in different devices, it takes very different parameters. Right? These get char, open, init, these APIs from different devices, they are very similar. The number of parameters are even the same most of the time. Okay, but that control can be very different. The control interface in different device drivers take different number of parameters for different purposes. So control is the ad hoc design. Right? So this generic interface hides all the dirty work, the ad hoc designs in the control interface. Okay. Everything else is quite standard across different devices. Okay, so another point to notice is that there are synchronous APIs and asynchronous APIs. Right? You can have a synchronous I/O interface, and if you're using a synchronous I/O interface, a process is blocked until the operation completes. Right? When you're using an asynchronous I/O interface, a process continues to execute and get notified when the operation completes. And this pattern is widely adopted everywhere. Right? So I think the example that's close to everyone, I guess, is the JavaScript that runs in everyone's browser. Right? JavaScript is heavily asynchronous. Okay. Everything in almost everything in JavaScript is asynchronous. So if you want to perform any function operation in JavaScript, you need to register a callback. Okay, you register some event and a callback. When an event happens, it triggers this callback. Okay. And JavaScript is the main scripting language that people use for your browsers. Okay. Synchronous I/O. Right? It is a very classic, right? It was first designed. Right? Asynchronous I/O comes later. Synchronous I/O comes much earlier. And synchronous I/O just means that when you perform an I/O, either read or write, you get blocked there until this operation finishes. Okay. Asynchronous I/O meaning that if I want to perform a read, but the device maybe is not available or something, I just say that I want to perform a read. Let me know when the read is ready. Okay, and I'll just continue to do whatever I want to do, and I will get notified when the read is ready, and I'll just perform the read. Okay, these are two different ways to perform I/O. Right. In Xenu, we use a simpler type of semantic, which is synchronous semantics. Right? It makes the implementation much simpler. So I'm not sure whether people have you guys taken some front-end development, these kind of courses? Are there some front-end development courses here?
There are classes, but I don't think it's part of the main track.
I see, it's not main track. I see. Yeah, so if you have taken front-end development course and you have written JavaScript, you will know that asynchronous code is very, very difficult to get right. It's very difficult to debug when something goes wrong. Right? So there is this famous thing that people, front-end developers used to refer to the problems that they encounter in JavaScript. They call it callback hell. Right? So when a bug happens in some callback, that there are multiple layers of callbacks, and you don't know when the bug happened and where it happened, and it's very hard to debug. Okay. Yeah, so in Xenu, luckily we use synchronous semantic. It's much easier to develop and debug. So we avoid the asynchronous callback hell. Okay. All right. Yeah. So the synchronous semantic in Xenu says that when the processor attempts to receive incoming data from a device, the process will block. It does not continue to do other things. It will just wait until my data is read. Okay, and when the process attempts to send outgoing data to a device, it will block there until this data is sent out. Right. It will block until data can be transferred or placed in a buffer where it stays until the device finishes transferring it. Okay, so if, let's say, the device temporarily is not available for the process to use, the process will wait, will block there and wait until the device becomes available. Okay. All right, so coordination of process performing synchronous I/O, right? Because these devices, they are sharing, they are shared by all the processes in your OS, right? So apparently, using this device need to be synchronized, right? So one process uses the device, the other process need to wait, right? And that's why you use semaphores to do this, right? You have semaphores, you use semaphore to synchronize processes that are trying to use some shared resource. Okay. Right. Oh, yeah. Yes, there's no need to invent new coordination coordination mechanisms, and we have already studied the message passing, semaphores, and suspend and resume. I think message passing we explained it briefly, right? So later we will catch up on this. I think we will spend half a lecture or so to go through the details of message passing. All right. Semaphores we have explained in detail. Suspend and resume we have already also explained in detail. Okay. So how to implement device-independent I/O in Xenu? Right? We have explained what is the interface of this device-independent I/O. Right? Okay, how to implement it? Right? So the application process will make calls, invocations, right, to the device-independent functions: read, write, put C, get C. And those functions we listed. Right? And one of the parameter of this function is a device ID. Right? So you can use macros to define the device ID, like Ethernet, right, or console. Okay? Right? Represent the network and your console. Okay? So these functions will take your device ID as parameter, and this device-independent function that gets invoked here, right, for example, the read function, will use a device ID to identify the correct hardware device. Right? If I'm using Ether, then I'm going to see that the user is trying to use a network card. If it's console, the user is going to use the console. And use this device ID to find the appropriate device-specific function to perform the specified operation. This is very straightforward, right? When I call read with Ethernet as a device ID, it means that I want to use the network card's read operation, a read function. Right? If I call read with a console as a parameter, it means I want to use the console's read operation. Okay. It's in Xenu you have this ETH read, right? In console you have TTY read. Right? So these are read functions defined specific for the network and the console. Okay. All right. So that is how user program interact with these device driver interfaces. Okay. Now the next step is now we have these devices interface like read or put C or get C. How to map this generic function to device specific function. Okay. So this read, right, there will be a device-specific read implementation of this generic read interface. Okay. So what we do is that we use a mapping, right, a two-dimensional array as an essential mapping called device switch table. And a device switch table, right, it's initialized at compile time, and it has one row for each device. Right? Every device has a row, and one column for each possible I/O function. Right? In Xenu source code, you can see this table. Right? So for Ethernet, for the Ethernet card, you have one row. It starts with, for example, the Ethernet itself, and then it has a list of operations. Okay, read, write, get char, put char. Each of it is a pointer to the implementation of this function for this specific device. Okay, and an entry in the table points to a function to be called. Right? A get char interface in this table, right, is a pointer to the implementation of get char for this device, maybe Ethernet or maybe the console. Okay, the device ID is chosen to be an index into this row, into the rows of this table. Okay. So we also mentioned that there are some ad hoc, some operations might not be supported for different devices. Okay? We mentioned that maybe for monitor, most of the time it only uses put char and write, right? Because you don't read too much from the monitor unless it's a touchable screen. Okay, these are other examples. Right? For example, seek operation does not make sense for a keyboard, does not make sense for a network interface, and does not make sense for a audio output device. It only makes sense for those devices that's like a big array, such as SSD, such as hard drive. Okay. Close, you cannot close a mouse, so it also does not make sense for a mouse device. And if some function does not make sense for some device, it's just unsupported. Okay. All right. Yeah, so to avoid special cases in the code, you make sure that each entry in the device switch table points to a valid function, but you use special functions for cases where operation is not supported. Right? So every function pointer is still, every slot still has a function pointer that is a valid address. But for example, for a mouse, its function pointer, its close function pointer, points to a special function says that this functionality is not supported. It maybe just print out one line saying that this is not supported functionality. Okay. Okay. There's special interest used in the device switch table. IO null. It means that there is an innocuous operation, right? So for example, open for a device that does not really require opening, right? And it simply returns OK. Right? The other is IO arrow. Right? It's used for an incorrect operation. For example, if you have a put char on the disk. Let me see. Let me think. I forgot this part why. So if you can theoretically you can treat disk as a bit byte stream and use seek and put char to write characters to disk, right? They should be fine. The incorrect operation would be for example, close a mouse, right? Seek on the keyboard. These will be incorrect operation. If you invoke these operations, they should point you to this function IO arrow, and they should return an arrow. Okay. All right. So IO null just means that this is equivalent to a no op for this device. So it simply returns OK, succeed. Right. So this is an illustration of the device table, right? So you can have a console, serial device 0, serial device 1, Ethernet, and the functions, these table entries here, open, read, and write, they are filled with the function pointer to the device-specific function implementations. Okay. For example, the open slot it contains a function pointer pointing to the TTY function implementing the open functionality for console. And similarly, the other device is the same. Okay. Yeah. So a computer may contain multiple copies of a given physical device, 2 network cards, 2 disks, 2 monitors, and you have 1 copy of a device driver code for each type of device, and use the same code with multiple devices. This is okay. Okay. So as long as these 2 devices, their table entries are pointing to the same functions, then you do not have a duplicated code for different devices. Okay, yeah. Yeah, we mentioned this, right? Instead of creating a device driver for each physical device, if there are multiple devices of the same type, for example, multiple hard drives, multiple SSDs, then the OS maintains one single copy of this driver for all the devices of the same type. Okay. All right. Yeah, to handle this, so a device driver must know which physical copy of a device type to use, right? So you have multiple disks. The device driver need to have a parameter that you can use to tell it which device, which hardware, which hard drive is being used. Okay, so you need to keep information about each physical copy of a device separate from the information for other physical devices. And yeah, so in Xenu, right, you assign each instance of a replicating device a unique number, right? Disk 0, disk 1, disk 2, right? It's known as its minor device driver, minor device number. And you store the minor device number in the device switch table, right? For 2 disks, you have a minor number 0 and 1. For network cards, you have number 0, 1, 2, right? Okay. So these minor numbers only distinguish among devices of the same type. Yeah, but these are the details. I think most of the concepts we have already explained at high level. And these are the details that if you read the code yourself, you are easy to tell that how they are implemented. Okay. And so the examples include 0, 0, 0, 1. These are the hard drives. You have 2 different hard drives. One is 0, 0, the other is 0, 1. You have 1 console and 1 network card, like Ether. Okay. Yeah, so the number of rows to allocate in the table, unique values of random device names, and the minor device numbers, they are all done automatically when the system is initialized. Right? So there is a configuration program takes device information as input, including names to be used for devices, and generates the definitions and device switch table entries automatically. Right? This is typically done when the system initializes. Okay. Yeah. I'm not sure how many of you have read the initialization code of Xenu. If you have read the initialization code of Xenu, you will see that there is a part of it performs the initialization of device drivers, of hardware interrupt handlers, and so on. It is done automatically. Okay. Yeah, so I don't think we want to go through these details, right? But yeah, I would suggest you read maybe Xenu code yourself, right? So this is what is during system initialization when we configure these device drivers. So what is really done? Right? During configuration, you list the devices in the system and give each one a name, like console, network, 0, 0, 0, 1. And specify the type for each device, and specify the driver functions to use for each operation. Right? These are all done automatically in the configuration operations. Okay, it generates 2 files: a file named conf.h and conf.c. Right? They contain the declaration of data structures used in the device switch table, and the definition of function of the device switch table with initialized values, including the minor numbers. But these are all implementation details that you can read in Xenu. Okay? All right. At a high level, when the system initializes, you also initialize the I/O subsystem. And at system startup, you initialize the interest in the device switch table. Right? It's already initialized. And you initialize the interrupt vectors Okay, and the init function is called for each device, which initializes both the device hardware and the driver. And whatever setup that needs to be done for each device will be performed at the beginning of system startup. Okay, so I think in the current lab you don't need to create a device driver. You just develop a file system. But this is the old lab. Okay. All right. Let me see. Do we have time to go through? Oh, yeah, we have one example. Okay. Almost there. Right. So we'll use one example to explain how a high-level I/O function is implemented. Right? Remember, the high-level I/O function is the function that the application uses. Application directly invokes. Right? And these high-level functions include open, close, read, write, read char, put char, and so on. It takes a device name as an argument, use a device switch table to choose a device-specific driver function to use, and it invokes a driver function. It invokes read or write. Okay. So yeah. So the high-level function uses one level of indirection to invoke an underlying driver function. Let's look at the read. Okay. So this is the read function. It reads one or more bytes from one device. Right. You can see that this DID32 is the descriptor of the device. Right. This device descriptor is used to identify which device you are trying to call in a device switch table. Okay? And the second parameter, because you are performing a read, so you're giving it a buffer, right? We are going to read the data and put the result of this read into this buffer. Okay? Count means that how long I want to read, right? Or length of the buffer. How many characters I want to read. Okay? And these are initialization. I use mask to disable interrupt, and I use int32 to return remember the return value. Right, these are all standard operations, standard error checks. Okay, so these two lines are important. Right, these two lines are the core functionality of this read function. Okay, what does this mean? So we call this read. It's a generic function interface, and when you give it a device driver, it's going to first use a device switch table to find which device you are really trying to read from. Okay, this first line is to get the device that you are really trying to read from. Okay, the second line here is to use this device. Right? Remember this device points to a row in the device switch table, and inside it, it has a list of functions defined. This list of functions are the device-specific implementations of the generic functions read and write. Right? So, for example, this one, dv read. Okay? This is the device-specific read function implemented for this device. Okay. Right. So using this is a high-level I/O function. What does it mean, right? So the user application does not need to worry about which specific hardware function to invoke. It doesn't matter which device the user application want to read from. It always calls read with the buffer and the device ID. Whether I want to read from the keyboard, whether I want to read from disk, whether I want to read from some other devices, I always use the same interface, which is read, device ID, buffer, and the length of the buffer I want to read. Okay? And then inside this function, this implemented in the OS, it figures out which of the device-specific implementation of read function needs to be used through this device switch table. Right? It figures that out and invokes that device-specific implementation of read function. Right? Maybe it's a console read, maybe it's a keyboard read. Right? Okay. All right. You can imagine write, open, they are all implemented in the same way. The open takes a device ID, and inside it, its main functionality is to find the device-specific open function and invoke that function. All right. Okay, that is the device driver, high-level explanation of device driver. Right now we'll, let me see, what time is it? Okay, actually let's end here. Right? So next lecture we'll go. So this lecture I think is a little bit high level, right? So with not that many examples, right? So it could be hard to understand. So next lecture we'll look at a complete device driver. That will be I think more interesting and easier to understand. Okay. Yeah, that's it for today. If you have other questions, you can come up and ask.